Hey everyone, today I'm going to be introducing you to something called a vector field, which is a new type of function. We're going to be using them here and there throughout our course, and the purpose of this short video is just to give you an introduction to the definition and a quick example. All right, let's get started. So to get started, here's a picture of the continental United States with some arrows drawn on it, and looking at this picture, it might seem like something maybe you've seen before on Weather Channel or something like that. And the game we're playing right now is, what's the function? In other words, there's a function being described by this picture, and what is it? In particular, what are its inputs and outputs? Okay, so just in case you can't see from the video, let me zoom in a little bit here. What's going on is that at every different location in this map, there's an arrow, and the arrows are, if you saw the scale a second ago, the arrows are telling us the wind as a vector, right? They're pointing in a direction, which is telling you the direction in which the wind is blowing, and the length is meant to correspond to the speed of the wind. So the input is location, which you might indicate by providing like an X and Y location or latitude and longitude, if this was on a globe. And the outputs, well, they're vectors. They are indicating the speed and direction of the wind at every different location on the map. So this is what a vector field is. It's a function of, in this case, x and y, whose output for every x and y is a two-dimensional vector. And they're used to describe lots of different physical quantities. For instance, here we have a wind map, but you could also use it to describe the flow of fluid, such as air through a room or water in a stream. And what we're going to spend some time doing throughout the rest of our course here or there is trying to use our mathematical techniques to understand qualitative properties of the things that are being described by these vector fields. For instance, if we zoom in on this picture again, it looks like there's something going on around here where the vectors are pointing in a counterclockwise spiral, maybe around this point here. So maybe there's a storm here or something that's causing this like vortex of wind. And one of the things we'll be doing is using calculus to quantify how much a vector field is rotating, like this one is here. Okay, so that's the overview. I feel like we should talk a little bit about what the notation is for a vector field. So they're functions, and we're going to write them like this. Typically, we'll write them with capital letters, something like F. And the vector field from the previous example was a two-dimensional one, but we could have three-dimensional vector fields too. Vector fields defined on R3, so the inputs would be X, Y, and Z, and the outputs would be three-dimensional vectors. So the inputs are X and Y, and the outputs, well, it's a vector, and the components of this vector can be things that depend on X and Y. So we typically will write them like this, something like P of XY and Q of XY. Those are both functions of X and Y. So the last thing for us to do is just a quick example of sketching vector fields. So here are two rather simple vector fields, and I'm going to walk you through what it's like to draw them, kind of to produce that same sort of picture of the arrows that we saw in the wind map from earlier. So here are my axes, and let's just draw this first one, F. So the way we draw vector fields, we draw the vector f of xy. If x and y are a specific point, we draw the vector f of xy as a vector with its tail at the point xy. So let me show you what I mean by that. Let's just pick a point, say 1, 2, f of 1, 2, according to this formula, should be the vector 2, 0. So to draw this, I'm going to go to the point 1, 2, which is here, say, and I'm going to draw a vector that points in the x direction by 2 and in the y direction by 0. So I've done that here. This is f of 1, 2. And that's how it goes. I just want to draw more of those. Let's say we draw f of 1, 1. I take the point 1, 1, and I plug it into this formula, and I get the vector 1, 0. And so I'm going to draw the vector 1, 0 with its tail at the point 1, 1. 1, 1 is here, and the vector that points in the x direction by 1 looks like that. And for one more example, let's draw the vector f of 0, -3. That'll be the vector negative 3, 0. And that'll be a vector that I draw at 0, negative 3, which is, let's say here. It's a vector that points to the left by 3, something like that. To draw the entire vector field, we'd want to put vectors at lots of different points. And you don't have to go crazy, maybe drawing a grid like I've drawn x and y going out from negative 3 to 3 here. And maybe at every grid point here, we would draw the corresponding vector. And also, maybe after doing a few more examples, we'd start to notice a pattern. Looking at this formula, the vectors are always going to point strictly horizontally, meaning either to the right when y is positive and to the left when y is negative. And moreover, the length of these vectors only depends on the y-coordinate. What that means is that all of the other vectors at the height of y equals 1 are going to be this same vector, 1, 0. So I can draw all of those in like this. Similarly, at y equals negative 1, they're all going to be the vector negative 1, 0. At y equals 2, they're all going to have length 2. Things are going to overlap a little bit, so maybe you want to shift them so they don't hit each other. Actually, to make your picture better, maybe instead of drawing them at every grid point, you would just space them out a little bit. The point isn't to draw every vector perfectly, but instead to show what the pattern is. The last thing I'll point out for this example is that if y is equal to 0, for instance, if we're looking at the vector f of 1, 0, well, that is the vector 0, 0. And we draw the 0 vector just as a dot, so we'll have those at all of our grid points along the x-axis. Okay, so I cleared some space here. I'm going to draw this second vector field, G, in a second, but maybe you want to pause the video and try it yourself first, just to get a little practice before you see me do it. So here are our axes. We're going to draw the vector field in orange. G of x, y is 0, y. And the procedure is just the same for every point. So here's the point 1, 1, for instance. We plug in 1, 1 into this vector field, and we get G of 1, 1 is the vector that points in the y direction by 1. So it'll be pointing up like that. Keep going. G of 2, 1 will be the same vector, right? Because again, just like the other one, there's only this vector only depends on y, but now it's just pointing vertically. If we're looking at a point like negative 1, 2, if we plug that in here, we'll get the vector 0, 2, which points up with magnitude 2. And the rest goes similarly. When y is equal to 0, the vector field is the 0 vector. When y is negative, the vectors will be pointing down. So for instance, at 1, negative 1, the vector is pointing down with length 1, like this. Okay, so that's what this vector field looks like in orange. The last thing I want to point out here is that just looking at these two vector fields, I mentioned earlier, we're going to want to try to figure out when a vector field is rotating. And it looks like this green one, there's some rotation going on. And I'm not being too precise about what that means, but you could imagine if this was describing the movement of water in a shallow pool, and we're looking at it from the top down, if you were to put a little paddle wheel, something that could rotate at the origin but not move, it would rotate clockwise, just being pushed by these arrows. Whereas if you did the same thing here, if you put a little paddle wheel at the origin, it wouldn't rotate because the vectors are pushing it sort of evenly in both directions of rotation. So this one's not rotating. And so in our next video about curl, we're going to be spending a little bit of time quantifying what exactly this means. So that's the end of this one, but I'll see you in the next one.